Edward Kosior is Managing Director of Nextek Limited. Edward has more than 37 years experience in plastics and rubber and has worked globally with government and commercial organizations, including for more than a dozen years working with the recycling of plastics packaging, including the design of many modern plants and achieving various patented recycling breakthroughs. He previously also was in academia, served as Associate Professor of Polymer Engineering and the Director of the Polymer Technology Center at RMIT University in Australia up until 1997. And in 2004, he created his current company, Nextek, to provide consultancy services to assist the development of strategic approaches to sustainable packaging, waste reduction, and minimal life cycle impact. He's truly a force on the global stage, and I'd like to introduce Ed Kosior.
Thank you, and thanks to Doug for inviting me to come and speak. It's my first Plasticity event, so I'm really pleased to be here, and it's great to be back in the US again. We come here reasonably often. Now, one of the things that Doug asked me when we started to talk about this conferences was, what are you going to talk about? And I said, my passion is that every plastic should have a home when it's designed and built. And so we decided to title this, Every Plastic Can Have a Circular Destination. So, and I think this is something that I've believed in for a long time. And I've come from a university background where we basically did lots of research and really got very few results in the real world. And so I was really keen to move from academia and actually to make a difference in the world by designing recycling factories. So that's one of the things we do. We design recycling technologies that are implemented by businesses, and we also work with brand owners to help them design new products that are more recyclable. And we also work on improving the performance of recycling plants. So this takes us to lots of places. We also run workshops in this area. I think next month we'll be in Colombia. I've already had our first speakers from Colombia. But equally, we're running programs in Australia, Malaysia, India, and UK as our prime areas of operation. So we get to see lots of different things and understand what's happening at different levels. And today, I hope to show you a little bit about what we might think of as the leading edge of recycling technologies. I want to take people on a bit of a journey about what a recycler does, because not everyone will know what happens in recycling plants, and then talk about the opportunities for better design in helping efficient recycling. And let me tell you, if we actually make products that fit a criteria, there's a huge impact on the recycling plant. Make no mistake, it's huge. And I've got some case studies about difficult to recycle materials, and these are out there because they've been designed this way without really the thought about how to recycle, or there's some been big barriers to recycling, like black plastics. And then I'm going to finish up on strategies of how we can perhaps do this a little bit better. Okay, so the first thing to look at is what sort of things should we be doing if we want a circular economy in plastics recycling? And the best thing that we can do is make recycled plastics that are equivalent to virgin materials. So we can actually replace them. And there are now companies being built in Europe with exactly this purpose. They're not recyclers of plastic. They've actually said, we want to make recycled plastics from the post-consumer stream that are equivalent to virgin resin companies. So this is actually quite a big thing. One of the other principles is that the yield of an operation should be high. An ideal scenario is when you put 1 ton in, you should get the maximum out. Now, the best plants around the world can get about 75% of the incoming material out as product. In some cases, though, it's 50% or even less. So can you imagine? You may put 20,000 tons of plastics into a plant and you get 10,000 tons of product and 10,000 tons of other material which you can't recycle. And that comes back to this whole issue about collection and recycling. The expertise of recyclers has to be fantastic. When you think they get a mixture of materials and they have to end up with something that's got to be 99% pure. And in the case of making food-grade plastics, the specification can be as high as 99.9%. So we really have to improve the efficiency of sorting to make these pure materials, because if we're going to recycle materials to replace virgin, which is the most economic thing for recyclers, and we've heard that in the world of business you have to be competitive, you have to make things that are extremely reliable and safe, food safe. And so purity is right up there as one of the key issues. And then the plants have to be big scale, and by big scale I would say 2 tonnes per hour. We often get asked by companies, oh, we want to build a recycling plant, and when we work out the amount they want to recycle, it turns out to be quite small. But a world-scale plant is 2 tonnes per hour, which equates to about 15,000 tonnes per annum. So unless you're running that plant, you actually be uncompetitive with other plants. And the other thing is the plants need to be simple and stable to run. And they need to be simple to control. If anyone goes to a recycling plant and has a look at the equipment used, you'll find equipment that's probably cost $20 to $30 million in that plant. And do they have chemical engineers with degrees running that equipment? No. No, they have people who have very basic skills of reading and writing and understanding of machinery, and they're running very expensive equipment. And so the key thing is this equipment has to be very stable and very easy to control. And that's what lots of equipment has developed into. Then the other thing is you need a steady supply of material to the plant. We often get asked to design a plant, and the first question we ask people is, do you have the material? Do you have all the contracts for the supply of the material? Can we see the material? Because this determines what you actually design in a plant. And if you don't have that, you really will run into trouble. And you can't just build a plant and say, let's hope for the best, because it doesn't work that way, because you will run into trouble. And in a recycling plant, every possible contaminant that you can find has to be removed. And it's got to be done in an efficient and safe way. And that includes inks. And we had a great story today about making sure people leave caps on recycling, or in fact that was at the ANTEC conference. Things like caps on PET bottles are essential now in recycling operations because they represent a revenue stream. So, and ideally in a circular economy, we should be able to do this time and time again with stable recycling processes. And here are a series of steps that recyclers have to undertake in order to recycle materials. These are the basic things. So they involve debaling, removing sand, taking out loose labels and metal, sorting the material into product streams, cutting it up, washing it, and then sorting it again to take out the coloured materials, removing any metals that are in there. And then there's very often a decontamination step. And then we extrude the material into either granules or perhaps into, we may work with flakes. And then you have to do all the testing. So there's a lot involved there. And when you buy plastic materials as a bale, you not only get the bottles, and most specifications would say at 90% purity in a bale, then that's a good bale. So, and very often you'll get less than that. And so you get lots of other contaminants. In PET, there are lots of other things, for example, aluminum cans. You get detergent bottles, you get thermoform trays, you get paper products, lots of these get in. And these are bales that are purchased. When I started in recycling, I used to complain about the amount of water that was in a bale. So 8% of a bale is water. So if you're buying a bale, you'd have 8% of your money buying water. And I'd go to the suppliers and say, I want a discount. I want 8% discount because of all the water you've got. I don't want to buy the water. There was no discount, I can tell you. So you get the water. Okay. If we take recycled high-density polyethylene, and Tamsin gave us a great overview of what they're doing in California and other parts of the US. I want to go through some of the key requirements. And just to show you how difficult it is, if you like. First of all, if you're going to sell a material for a circular economy, it has to be consistent, it has to be a neutral colour, it has to have constant composition, and we might use melt index to measure that, and we have constant mechanical properties and low odour. All those are, if you like, the baseline, and you can't always get that. And then people want the price. They immediately say, oh, it's recycled, so it has to be less than virgin. But usually, it doesn't have to be very far below virgin resin. Then it makes it still acceptable. And if you sell recycled material in the normal market, for example, for pipe, you'll typically get 2/3 of the value of virgin resin. And for a recycler, that's a killer. They really can't make money if they have to sell at low prices. So that's quite difficult. So the big question is, can we do this right now? And I think to some extent Tamsin led the way. The answer is, for food-grade resins, the answer is no. But for non-food grade resins, the answer is yes, we can do it. And so this actually has encouraged a whole series of developments. Now, the bottles I'm showing you there are bottles that are going to be put on the market in Europe. They're also on the market here in the US. And there are two bottles there shown in colour. One has 50% recycled content, the other one's made from virgin. So I don't know if you can pick which is which. And in reality, it doesn't really matter, because most consumers wouldn't be able to pick the difference between them. And these bottles are now going back into the loop. So the company that makes these laundry products is now going to take their laundry product bottles from the market. They're going to put it through a process and put it back into the market again. And this is really what's happening both in the US and Europe, and this is going to be the way the circular economy will work. But just a few steps about recycling. The first thing that happens in a recycling plant, we put the materials into a trommel, which is like a big screen, and we shake it. We shake the material. And at that point, if you've designed a small bottle or made small products, they all fall through the system and go out to waste, or perhaps to a recovery system. And usually we either sort materials by hand or by machine. Just to give you an idea why we use machinery, you need 12 people to sort at 2 tonnes per hour. And that could either be positive sorting or negative sorting. This is really why sorting by hand is not an economic option. This is the way automatic sorting machines work. And this is a very old graphic, but it's a very nice one, because it shows you bottles travelling on a conveyor, a sensor looking at the polymer signature of the bottle, and it's determining, is this PET, high-density polyethylene, polypropylene, polystyrene, PVC, and then an air blast directing the material into another direction. This is how automatic sorters work, and they use the near-infrared signature to sort these materials. And the sorting efficiency is approximately 95% for nearly any modern system that you buy. And the other thing that happens in recycling plants, there's a wonderful separation process that relies on sinking or floating in water. Plastics lighter than water float, and the other ones sink. And this is used a lot in our recycling operations. And this is something that we rely on. And if we take the two important ones, PET sinks in water, and polyethylene and polypropylene float. And I'll mention why this is important in a second. If you take sports caps, there were a series of sports that came out, and they had a silicon rubber seal in them. That silicon rubber seal is like PET, heavier than water, and sinks to the bottom, which means that that seal will go into the recycling process. And when this happened, it caused chaos in the industry. Recycling in Europe stopped because of these silicon seals were contaminating the PET, and it caused all production to be contaminated. And so they had to introduce special machines just because of this sports cap was in there. And in the case of things like bottles with trigger packs, this is the traditional design of a trigger pack, where you have a metal spring, but you also have a acetal piston, and also a glass ball as a non-return valve. Now, when we started this investigation, we thought, what on earth are they using a glass ball for? Because no one actually expected to see a glass ball in there. So we were seeing glass fragments in the PET. Well, this is where they were coming from the glass ball. So why, did the designers think about this, that they were doing this? And of course, the metal spring creates lots of contamination as well. And here is a new design, a new trigger pack with no sinking parts. Every part was made from either polypropylene or a thermoplastic rubber, which could then be fully separated from PET and also compatible in a recycling stream. So that's what design can do. You can actually flip from a disaster to a useful product. Here are some things coming onto the market right now. On the left-hand side, you'll see that Ariel bottle, and then next to it is a Pantene bottle. Why are these going to be difficult? The simple fact is that they're made from white PET. And anyone who runs a PET recycling plant will say, after PVC, white PET is the worst thing they want to see. Because if you're going to make recycled PET bottles, white PET damages the clarity and creates haze in the bottle, so it's quite a negative thing. And then on the right-hand side, we've got some polyethylene bottles, and I'll show you a little bit about these. And these are all PET. So, on the left is high-density polyethylene, but it's a 3-layer one. And here's some flakes. You can see the flakes on the side over here, and you can see on some of them there's a black edge. And that's because it's a 3-layer product. In the middle is carbon black. But the people who run the flake sorting machines can't see the carbon black, so they keep sorting and say, oh, we've only got white milk bottle, but when they extrude it, they end up with a black streak through the whole thing, and it turns grey. And in the case of PET, these are bottles that are being introduced now. They look white on the outside, but on the inside of the preform, you can see here, it's black. It's for opacity reasons. And this one is actually white on the outside and the inside, but in the middle layer, there's a black streak for opacity. So what is the recycler meant to do with this? This is a recycling nightmare. So let me tell you, if whoever designed this walked into a recycling plant for PET, they'd get a very warm welcome, I can tell you. Okay, and here's another very new product coming from Procter & Gamble. It's just come on the market. It's a Lenore bottle, which is a fabric softener, and it has a full body sleeve. Underneath that sleeve is a white PET bottle, which is, we're saying it's not a good thing, but the sleeve is made from another material. And so when this material gets sorted, it's in fact a polyester, it gets sorted not based on the PET that's underneath, but based on the label. So there are confusing messages here. However, Procter & Gamble said, we've put instructions on the label to tell people to unzip it. And there's a zip along here. And so they say, well, all the consumers will unzip it, and so they'll separate the sleeve from the bottle. This doesn't happen, despite the best efforts of marketing. Now, one of the really important functions of plastics is to minimize food waste. And there's no doubt that the use of plastics improves the saving of a lot of carbon because we package food efficiently and it lasts much longer packaged in this way. And so you can see here, vacuum packaging increasing the shelf life of meat by 50%. The sirloin goes from 6 to 16 days. The flow pack, vacuum pack material, they can reduce food waste by enormous amounts by the functionality of that package. Now, this is causing a big problem in Europe because these thermoforms can be either 1 layer, 2 layer, or 5 layer. And give you an example, here's some of the structures of these materials. And why is this important? If you reprocess these materials, and I'll show you here, we conduct an oven test on what we call the monolayer material. You can see on the right-hand side, especially here, this is multi-layer material. it changes from the clear material, and after the oven test, the multi-layer components degrade to form very dark compounds. So the PET that's recycled is completely dark. So the use of PET multi-layer trays is a big problem, because when they sort them out, they look like they're PET, but it's like swallowing a poison pill for the recyclers. Okay, the other thing that's a big issue now is the creation of black trays. Now, I mentioned before, the way we sort plastics is by using infrared to read the signature. And of course, if you have carbon black inside a tray, all the light, the visible and infrared, is absorbed by the tray. So the tray doesn't give a signal back to the detector. So what we have done in a separate project is we've formulated a black pigment that can be detected by the infrared system. So it doesn't absorb in the infrared. And last year and this year, we'll see major trials of big brands using the so-called detectable black pigments. And so we're looking forward to this being rolled out in the near future. And this will become one of the simplest steps that we can do for recycling black plastics. Just change the pigment and it goes from unrecyclable to recyclable. And this is an indication of how this can happen. So you can see over here, this is what the camera sees. So you can see here's a black tray, here's a clear bottle, there's the outline of the clear bottle, and there's the tray. If this had carbon black in it, you would see nothing here. So this is showing you that the machine can see both materials, and at very high efficiencies as well. So what about the use of bottles? If we have a look at bottles, and I think I may have got my slides out of order here. Have I? No, never mind. The first one on the left is a sleeve bottle, and underneath it's clear. The next one is a food-grade milk bottle, and the one next to it is a food-grade bleach bottle, and then the last one's a black bottle. Now, one of the problems is in sorting, you may not get sorting in the correct category or the material seen at all if it was black. And so, especially if you take the milk bottle and the bleach bottle, how do you tell the difference if they both appear to be the same? So this is a problem, and if we use the new technology we're using for markers, and I'll show you a little bit about this, we're using ultraviolet light to shine on the labels of these bottles, and we're getting a signature in the visible and in the infrared. So that means we can tell the polymer and we can tell the visible signal. And by coding the system, we can actually tell what that material is used for. So this is showing you where we would put this into a plant, usually after a primary sort. And we can use 1, 2, 3, 4, 5 markers, and we have an increasing number of combinations. So if we use 3 markers, we have 7 codes available to us just from 3 markers. If we use 4, we have 15 codes. So it's a very flexible system, and so we can develop a protocol to identify materials. So we could say one color is for food grade, one is for non-food, one may be for bioplastics, and one may be for trays compared to others. And here are some of the materials we're using. These are just sat under a UV light, so you can see the variation in the materials. And we can see all of these by the use of a visible spectrometer at high speed. And this is the protocol we're proposing to use. So we're using, in this case, red for food grade, red and yellow for food grade pot stubs and trays, because in PET that's required as a separation step. And food grade and fully coloured sleeves are going to be using red and cyan, and then non-food would be yellow. And there are reasons why we're going for those particular colours, but I won't go into them. But I'm going to show you a video, and I'm not sure if I'm going to click this, whether it's going to work or not. Whoops, I'll go back. Okay. So you're going to see a video of bottles with sleeves on them, and we're going to do 2 tests. So let's see how we go. Okay. So we've mixed in bottles with sleeves of various fluorescent markers. And in this test, we're just taking out markers with a red signal. So when you see these bottles flying under the light system, you'll see that some of them being coloured. When they go red, they're being ejected. This is on the other side, and you can see the bottles falling that are not detected, and then on the right-hand side, the ones we are detecting. And this is being done at 2.5 metres per second, which is full production speed. And we're selecting only that red sleeve to take out. So you can see here, this is, first of all, a high-speed process and very selective. So we'll just have a look at the final product in a second as well. So the idea behind this is we could use a protocol to designate bottles of a particular type, and then we could extract that particular bottle at a particular sorting station. So if somebody said we want to take out a particular type of bottle, as long as it had a specific code, we could indeed do that. So you can see down in the bin, this is the ones we wanted. There's one error in there, which is a bottle with a red label. And that was something which is always can happen, but all the rest were exactly the one we wanted. And here are all the rest that we sorted from. These are all bottles taken out of a MRF. And now we've put the whole lot in again, just to demonstrate, and we've selected this time a blue label, a blue marker. And we just by changing the software, we can select the next bottle type that we're after. So again, you'll see what the results look like. 100% purity and the yield of 88% in this particular trial. And you can see some of them moved the other side, but essentially we're getting all the ones we wanted. Let me come to a more problematic area of talking about films, because films are a real problem in lots of areas. And when they're collected, they often are available at zero cost or at negative cost. People will give you mixed films for recycling, and they can be problematic. And the composition of these films is usually quite diverse. So there's polyethylene in there, low density, high density, polypropylene, and multi-layer. Now, most of the material is compatible polyolefins, PP and HD, PP and polyethylene. But the multi-layer materials can be a problem. And also the inks printed on those films can be a problem. Now, by carrying out sorting, and you can use sorting to sort films, which is something that hasn't been done a lot, but we've conducted trials and indeed designed factories that sort the film after shredding. You can get to much higher purities, but you lose a part of the material, and that's one of the costs of this recycling operation. And just to show you that some companies are taking advantage of this fact, for example, now Dow have worked on a project, and there's a pouch shown over there which does not contain any barrier material. So they're getting the functionality and the shelf life, but not using the barrier material, because if we can take out those multi-layer barrier products, then we can push this stream to a much higher proportion of fully recyclable materials. And we're not far away from that. And there's a project called Reflex. If you'd like to look it up, you can get the details of that. And in the study that we worked on, we were able to introduce processing where we could actually extract a lot of the volatiles on the extruder. So we're able to go from, for example, this is what material looks like without proper devolatilization in the melt, and we were able to go to films like this from that mixed material, and by using very high vacuum on the extrusion side, we're able to extract the inks and extract the volatiles and create highly usable films. So this is quite an important area, and I think we'll see more activity in this area. But it's probably one of the hardest to run economically because of the low value of the film. To the kitchen, when people use it, they say, oh, this goes in the recycling, this goes in the landfill. The other thing that will happen is in the supermarket, when they pick up a tray and they say, this is not recyclable, they'll put it back down again and say, well, is there another brand that is recyclable? And hopefully the market will move to products that are recyclable. And this is one way of carrying out consumer education, just by having a very clear labelling scheme. And then there are lots of industry groups in Europe and US, groups like APR in the US, the Association of Post-Consumer Plastic Recyclers, EPBP, which is the European Plastics Bottle Platform, PRE, which is Plastics Recycling Europe. They all have categorization. So if you're a brand owner, you design a product, you can tell instantly whether that's recyclable or not. And you can label it then. And that's a great thing for these people to do. And there is, these days, no excuse to make a non-recyclable package or a difficult to recycle package. There's no excuse. If you design it, you can redesign it. Maybe expensive, but that's your responsibility. Companies need to do it. And we should make recycling simple. Polypropylene, high-density polyethylene, and PET. This makes the life of the recycler a lot simpler, not various other materials. This is the dream, if you like, but that's the guiding principle. So, and then we should make mono-material compatible streams so that if you do have mixtures, then maybe you can extrude some of these compositions together. We're suggesting market technology. It's great to hear Tamsin endorse it. It's something that is, if you like, the next step in recycling, so we can fractionate these materials into higher value areas with less complexity. And then simpler decoration and inks that come off very easily, same with labels and glues. So these are all things that brand owners can ensure. It's a specification for them. And the good news is that lots of brand owners are doing this, but not all. And here's another video on on-pack recycling.
As the number of materials we can recycle increases, you may not always be sure what items of packaging you can recycle. So, it's good to know there's a simple labelling system in place to help you, which you'll find on the majority of popular and well-known products. The labels are a quick and easy way to find out what you can put in your recycling at home. Let's have a look at the three main labels. If it says widely recycled, it's a safe bet that you can just pop it in your recycling and it will be collected. You'll find it on things like cardboard boxes, glass bottles and jars, metal tins, cans and aerosols, and plastic bottles. Another label you might often see is the Check Local Recycling label, which appears on items like plastic pots, tubs and trays. These are things you can probably recycle too, but it's worth checking just in case. Take a look at the recycling locator at recyclenow.com to make sure they can be collected in your area. Lastly, things like packets and tubes of crisps, pouches from baby and pet foods, biscuit wrappers and toothpaste tubes might be labelled not currently recycled, which means they are unlikely to be collected. Look out for the on-pack recycling label on everyday products. It can help make recycling simple by letting you know what can be collected in your area. Remember, if you're not sure, you can check the recycling locator at recyclenow.com.
There's a similar one based on that in use in the US as well, and it can be used widely and internationally. Now, and also I mentioned that there are recycling guidelines. This is one graphic of one area for thermoforms. This has been put out by the Plastics Recyclers Europe, and they have a red, amber, green system. And you can go to all these design guides and they'll say, if it's red, it's a bad point. If it's green, it's in the good area. And if it's amber, then you need to check and maybe there are alternatives. So I just want to say that these are widely available and doesn't take much searching to find them. So just summarising, we need an urgent action agenda in order to address what we're trying to do on this planet. We really only have one planet. We're not going to go to Mars, whatever they say. This is it. This is our one chance. And in order to do the right things, we actually have to change the systems that are not working. And what I'm suggesting here, that in the packaging supply chain, we all have to work together. The resin companies, the brand owners, the recyclers, the consumers, they all have a part to play. We need to boost recycling rates. People need to know what to do. It has to be very simple. And we have to have a market for recycled materials. And whether we do it by market creativity in the free market or we do it by legislation, it doesn't really matter, but we actually need to do it. We need to stop the flow of materials that are not wanted. The one big thing I'd say is we should be seeing more big recycling operations, big plants like 100,000 tonnes, in order to make these systems competitive with virgin recycling. And probably something that we would like to see happen is that we'd like to see virgin resin companies buying recycling operations. Number one, they'll know how difficult it is, and then they can also make an offering of, do you want virgin, or you want recycled, or do you want a blend? And then they have the full market, and then they can actually bring their science and technology, which they develop in the virgin side, into the recycling plants, because the recycling plants are very often run on a low-tech basis. And the final part, and it comes back to the designers, is when you design a product, make sure you know exactly how it's going to be recycled. When you do that, when you know exactly how it's going to be recycled, the recyclers will have no problem. If you don't know or you're not sure, then you need to go back to the design table and say, let's pick one of the options and design it for one of those options. Okay, so that's my final slide. As I said before, every plastic item can have a circular destiny if we do so. And my little strapline here is, if we can imagine a solution, then we can do it. Indeed, we must do it. Okay, thank you.